Okay, these are notes for section 7.2c. So this is going over volumes, finding volume with known cross sections. So cross section is the shape that results if we were to cut the object in half and to look at the resulting shape sideways. So far, we found volume for an object using disk method and washer method. And if we were to look at the cross-section of these objects that's created using disk method or washer method, we're going to see that if we were to slice this object and look at it sideways, we're going to either be looking at circular disks or circular rings. Now, the reason that we're always getting circles is because we're taking a shaded region and we are rotating it about an axis of revolution. So anytime we're rotating an object or a radius across an axis, then we're always going to get circular shapes. So that is why with disk and washer method, we've always been involving areas of circles, either area of a large circle or with the washer method where we have to find the areas of two circles of different sizes and subtract out the whole. But this is not going to always have to be the case. It's not always that we're limited to only finding volume that involves the accumulation of circular disks or circular rings. What we're going to do is we're going to extend volume to other shapes as well, to other shapes that we know the formulas for. So for instance, squares, semicircles, or even triangles. A more general formula of what we've been doing so far, and we've talked about this, is that the volume has an area component and it has a width component. So if I want to find the volume, I can just think of it as adding infinite numbers of a given shape to produce the area dx. So that will give me the area portion and it will give me the width portion to create that third dimension. So what we're going to do is we're still going to start off with a shaded region, but now rather than acting as the portion that we're going to rotate about, this shaded region will now act as the base, and we will build this cross-section shape, this cross-section area on top of this base. Okay. So for instance, let's say we have this shaded region that's given, it's a half circle or a quarter circle in the first quadrant, and we decided to build squares on top of this. So we can see if we were to build squares, we're going to have to build squares of different shapes to fill this region. And if we build squares of different shapes from one end to the other end, then we're going to be able to create an object that has a three-dimensional shape. Okay. Now the ideas will still apply in the sense that if we're dealing with top and bottom, if we're dealing with vertical radius or vertical rectangles, we're going to have to think of everything in terms of x. We're still going to do top minus bottom. We're still going to have to find our bounds in terms of x. And if we're having to draw a horizontal radius, then just like before with disk and washer method, we're going to have to do everything in terms of y. So we're still doing right minus left. We're still having to find our y values as our bounds. Okay. So many of the steps will stay the same. We're still going to graph the equation. We're still going to have to shade the enclosed region. We're going to determine whether to use top, bottom, or right, left method. And we're going to have to choose the appropriate formula depending on which cross section that we're using. Either squares, isosceles right triangle, isosceles right triangle with hypotenuse as the base, equilateral triangle, or semicircles. For the most part, the radius, the rectangles that we draw from when we talked about area, the rectangles we drew, that rectangle represented height. With disk and washer method, that rectangle represented the length of the radius. But now, uh, but now the length of our radius or height or the distance from one end to the other will now represent the base. Okay, so the base either for a side of a square or a side of a triangle or a hypotenuse. So now they were going to represent a specific side of a shape. Okay, so next video we can look at some examples.